So in this video, I'd like to show you how you can calculate what happens when you flip a switch and start to charge a capacitor in an RC circuit. So here's the diagram of what we're going to be looking at right here. We've got a battery, voltage V, we've got a resistor of R, and we've got a capacitor of C. Now when we close this switch, what's going to happen is current is going to start to flow around this guy like that. And we want to talk about how the current and the charge and the voltage are going to behave in this capacitor over time. So let's take a look at that. So remember, at the very start, what we have are just two plates here in the capacitor, and they're neutral plates, which means at the beginning, it's very easy to start putting on positive charge and taking off negative charge. So in a sense, it looks as if a current is flowing right through the capacitor at the beginning with no problem at all. But what happens is over time, as you pile up more and more positive charges on this plate of the capacitor, it becomes harder to put on another positive charge because there's already charges there opposing it. And likewise, it becomes more difficult to put more and more negative charge on this plate over here because it's already got negative charge. So over a long period of time, what eventually happens is the capacitor reaches its capacity. It can't take any more positive charge and it can't take any more negative charge. And in the limit, what happens is the current doesn't only just get smaller, it disappears and goes to zero. So here's the picture. Right when you close the switch, the current is strong. And then as you wait longer, the current gets less, and then it gets less, and then it just drops to nothing. Okay? And so here at the beginning, right when the switch is closed, the capacitor behaves like it's a wire with no resistance at all, free flow. Then over time, as charge buildup occurs, there's some opposition. So it's almost like there's a resistance there. And then in the infinite limit, if you wait long enough, there will be no ability of current to go through at all. So it's like an open circuit. So we can represent that by these diagrams down here. Let me just sort of focus in on these guys. So the first one looks like this. Whoops. First one looks like this. You close the switch and current flows through the capacitor as if it's just a wire. Okay, so the current flow is really strong. Then if you wait a little bit longer, there's some opposition that builds up in the capacitor. So it's almost like, I'm symbolizing it here with a little resistance. And the current is now less because it's receiving more opposition in the circuit. And now if you wait long enough, what happens is you essentially get infinite resistance in that capacitor. I'm symbolizing it here by this really big, giant, bold resistor. But in truth, what happens is the circuit just becomes open. It will no longer conduct electricity at all. So this is what the picture looks like. Now over time, we can plot these things. So the voltage across the resistor at the beginning is large because the current just flows around from the capacitor through the resistor. And as it flows through the resistor, the voltage is large. So it's that full current times that resistance that gives us the voltage drop across the resistor. And so it starts out at a pretty high value up there. Now as time goes on, the current gets less, right? So if the current's less flowing across the resistor there, then the voltage drop is going to be less. So it'll be less. And then if you wait long enough, then there's going to be no current flowing across the resistor. So asymptotically, this will go all the way to zero if I wait long enough. So what's going to happen is the voltage across the resistor will just decline exponentially like that. What about the voltage across the capacitor? Well, in the beginning, the current flows through it really quickly, so there's no drop or there's no opposition in a sense. And so there is no voltage across the capacitor. It's as if current is flowing through there as if it's a resistanceless wire. Then over time, as opposition builds up, it's like it has a little bit of resistance. And so I've got some current going over some resistance, and so the voltage across it basically climbs. And then if I wait an infinite amount of time, what happens is the voltage of the battery here is basically just going to be mimicked by the voltage of the capacitor here. Even though there won't be any current flowing, the positive plate of the battery here will be like the positive plate of the capacitor here. The zero plate of this battery will be like the zero plate of that capacitor. And so in the limit, the voltage across the capacitor will go all the way up to the voltage of the battery itself. What happens to the currents? The currents behave according to this right here. First, they flow freely, and then over time, they begin to decline, 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 and in the end, there's no current flowing at all. So this is a qualitative picture of what happens. Now what I want to do is show how you can calculate these things if we have equations. So if we charge the RC circuit, we're going to have the charge building up on the capacitor. The charge will go like this. It's going to start out small, no charge, and then it's going to get bigger and bigger and bigger. And the charge in the capacitor is going to be related by this equation here. So capacitance is defined as charge divided by voltage, and so I can say the charge would just be capacitance times the voltage of the battery. Now it turns out I don't need that for some of the questions I'm going to be asking in a second, but it's good to know that. So what we can do is we can write an equation like this. The charge as a function of time is going to behave as the capacitance times the voltage in that simple circuit times 1 minus E to the minus T over RC, where RC is the resistance and the capacitance times each other. So RC, that product, together equals the time constant of the circuit. When RC is really big, then it takes a long time for the charge to build up. When RC is really small, then it will build up rapidly. So here's a specific question. How long will it take to get to 65% of the maximum charge, given this equation here? So graphically, what we want to do is represent it by this. Here's the charge, maximum charge there. Here's 65% of the charge, probably at about this level, okay? And here's the charging curve. It goes up like that. What we want to know is how long is it going to take, how much time here, to get to 65% of its charge like that. So if I draw a line over from 65% of its charge, wherever it intersects the curve, you can drop down and you find out that's the time it takes from 0 to get there. We can calculate that. So we set up the equation this way. We say this 65% of the charge is going to be the criterion at which we stop, okay? So we want that to be the charge on it. This is the total maximum charge that it could have. And then this is the function that basically gently goes upward like that. That's this function that goes up like that. This function right here, okay? That's given by this. Okay, we set up this equation. We see that this QC cancels with this QC. So I have 0.65 equals 1 minus E to the minus T over RC. I subtract 1 from both sides, and I get minus 0.35 equals minus E. And then what I can do is multiply both sides by -1, so this becomes positive and that becomes positive. Now I can take the natural log of both sides to undo the exponential, so I get natural log of 0.35 equals what was in the power up here for E, minus T over RC. Now I multiply both sides by RC, bring the negative sign over. So minus RC times the natural log of 0.35. The natural log of 0.35 is going to be some negative number, so these two negatives will cancel and it will become positive. That will give us the time it takes to get to 65% of the maximum charge that the capacitor could hold. So that's how we solve a problem like that. Here's another example. What about the voltage across the capacitor? What does the voltage do? Well, the voltage is going to behave like this as well. Okay, how do I solve that? Basically, I set up a similar equation, but now instead of using 65%, I'm going to use 50%. So if this is the total voltage up to the maximum, then 50% would be right up to there. I draw a line over here, drop that down. That's the time I'm looking for, T50, the time it takes to get to 50% of the voltage. So here's our equation, like that. I put in 0.5 as my goal, 0.5 volts of the maximum voltage, whatever V is. I cancel it on both sides, and I do similar types of math, right? Grinding it down in the same type of way, and I would get something like this. So what we've talked about is how a capacitor in series with a resistor behaves when we close the switch to charge it. It gradually builds up charge. It takes a while, but current flows very quickly at the beginning. And then we've gone over an equation that can tell us how to calculate various amounts of either charge or voltage across the capacitor as a function of time. Hope this has been helpful.